In this video, I'm going to go over what is a vector space, what is a linear combination of vectors, what is the span of vectors, what does it mean for vectors to be linearly independent, and what is the basis for a vector space. And I want you to be very impressed that I put all that stuff on my chalkboard. That was a pain in the ass, but the things I do for you. So, first off, vector space. If you've taken ring theory, group theory, or you're in ring theory, the idea of defining an algebraic structure shouldn't come as a surprise or shock, or this is not something new. Vector space is just more complicated because you've got more bells and whistles going on. So we have a vector space is a set of vectors. They're called vectors, but they can be anything, any set of objects that satisfy the following set of rules. 9 times out of 10, the vectors are going to be normal vectors like you're used to, but if I can have an example with apples and oranges if I define things correctly. A field F of scalars, that just means numbers. A field typically will use the reals, but a field just is a ring on steroids. It's got addition, multiplication, and it's got commutativity and inverses and a whole bunch of good stuff. A binary operation just takes two things and spits out another one. Addition is typical. We're also going to have multiplication on here. But let's go over the rules, what they have. We need plus to be commutative, so v plus w is the same thing as w plus v in terms of adding vectors. It's associative, so how you group them doesn't matter. And we have an identity. Scalar multiplication is commutative. 1, which is the identity in your field, the multiplicative identity from your field, times v gives you v for all little v and big V. So for every vector, 1 times the vector gives you your vector back. Scalars distribute over plus, and vectors distribute over scalar addition. So that just means, I can try to draw it, but it turned out crappy last time I did it. So if I said A times V plus W, or V plus W are vectors, I can distribute the A. Or if I've got V times the sum of two scalars, A and B, I can distribute those. So, let's look at some examples of vector spaces. Now we have our normal one. Vectors are just normal vectors that you know and love. And R is my field. That's supposed to be the funky R for reals. So that's, you can have them as row vectors or column vectors. And so that's, Matrices can be vectors. Think of them as vectors that have just been kind of folded up. So a 2 by 2 matrix is kind of the same thing as a 1 by 4 vector or a 4 by 1 vector. The point that's important with vector spaces is the idea of slots, individual slots that don't interfere with each other. So if I have 4 slots written as a column or a row or in a square, it doesn't matter. I've got 4 spots, 4 slots, and they don't mess with each other. Unless you multiply them, but that's a different story. So, another possibility is polynomials, the set of polynomials, because if you think about the coefficient for x cubed, the coefficient for x, the coefficient for x squared, I missed that, and constants, those are their own little slots when you add polynomials together. So that's another type of vector space. When we write these things, go to the next slide. As far as I'm concerned, these 4 examples are the same vector in the same vector space. We're over the reals, and we have 4 slots. We have 2, 3, 5, 6. 2, 3, 5, 6. Oh, look, the same numbers. 2, 3, 5, 6. Oh, cool. 2, 3, 5, 6. It's just the way you present it. I prefer column vectors over row vectors because when I see a row vector, I'm not sure if that's 2, 3, 5, 6 or 23, 56. And putting commas in there start making you think different things that you shouldn't be thinking. So I prefer column vectors. Linear combination. A linear combination of vectors is where you add the vectors up and where you multiply each of them by some scalar. So A1, V1 plus A2, V2, yada, 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 A and Vn. So all the AIs are scalars, all the V's are vectors. An example of that, let's say I've got V is this vector, 1, negative 1, 2, 3, and W is 3, negative 3, 4, 1. I want to do 2 times V plus, tongue-tied, 3 times V plus 2 times W. So if I have 3 times 1 plus 2 times 3, I get a 9. 3 times negative 1 plus 2 times negative 3 is negative 9, etc. So that's what I mean by a linear combination. The span of a bunch of vectors is what can all those linear combination of your vectors reach. Okay? Like, for example, if I'm in R3 and I have the vectors 1, 0, 0 and 0, 1, 0. So that means I can get to anything in the plane, the normal XY plane, because I have 1 in the X slot and 1 in the Y slot, but I don't have anything in the Z slot. I can't add those two vectors or linear combinations of those two vectors and get 1, 1, 1. I'm stuck in one plane. Whereas if I wanted to see if I can get to the spot 2, 3, that's easy. 2 times one vector plus 3 times the other, and I can get to that spot. We denote this as span of V1 through Vn. Sometimes I might use a curly brace here or an angle bracket. Depends on my mood. So let's look at an example. One question we might ask ourselves is a vector in the span of some other vectors? So let's say we have these two vectors. And I want to know if, okay, I'm not saying this right yet. I want to know, so the span of V and W are all the vectors AV plus BW, and they're in R4 because we have 4 slots. Is -3, 3, -2, 7 in the span? Can I write AV plus BW and get that vector? Putting V and W in there, I'm saying A times this vector plus B times that vector gives me this vector. I now have a set of equations. I've got A plus 3B equals -3. Negative A minus 3B equals 3, etc. So I can use my augmented matrix and go, okay, I've got one. Put this in row reduced echelon form, see if I can solve and get a solution for A and B. I get this, which means it's in the space. It's 3 times V minus 2 times W will give me this vector. Let's try a different one. Suppose I have 2, 5, -2, 7. And I want to come up with a linear combination for that. Set up my set of vectors, put it in row echelon form. I get this picture, but that row right there is telling me that 0 equals 1. So this vector is in the span if 0 equals 1, which it doesn't, so it's not. Linearly independent. The idea of linearly independent is to try to get rid of redundant information. Okay. The definition is if the only solution to A1 V1 plus A2 V2 blah 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 blah, blah A and V and equals 0 is if they're all 0, that means they're not redundant. If I can write these where some of these A's aren't 0, then I can write one of the vectors as a linear combination of the others, which means I don't need that one. So here are 4 vectors. I want to know if they are linearly independent. So I would set that example, A times this plus B times this plus C times that plus D times that equals 0, and see what I get. Wow, that took up a lot of space. So making it smaller, put it in my matrix, which means I basically have zeros all here. Remember my equations, this is all zeros. Row echelon form, I have a solution. So if I think of this as A, B, C, D, that means D is my independent variable, which I didn't write here somewhere. D is some S, A is 3S, B is -S, C is... So I have a bunch of combinations. 3S minus S minus S is a solution to the set of equations. If S doesn't equal 0, it's non-zero. So another way of writing this is S times the vector. So the solution space is the span of that one vector. But that's going off on a tangent, no pun intended. The problem is I have a solution that's non-zero. So these vectors were not linearly independent. But if I take one of these away, just randomly took one away, and try this, and put that in row echelon form, my only solution is A equals 0, B equals 0, and C equals 0, because I don't have a D now. So these 3 vectors are linearly independent. A basis V is a set of vectors that are linearly independent and spans V. If a vector space is finite, we say its dimension is the number of vectors in a basis for the space. I say a basis because there are infinitely many bases for any given space. Just depends on which ones you want to use. These three vectors, we found out that they were linearly independent. So they are the basis for some vector space that's three-dimensional. I don't know what it is, but they live in R3, and there are only three of them, so it's only three-dimensional. The vectors whose columns in row-reduced echelon form have pivots form a basis. The ones with pivots are the ones that are linearly independent. So let's go back up here. Way back here. Looking at this, and they're different subsets of the four vectors that will be linearly independent, but having squished these four together, I know that the first three are linearly independent, and this last one can be written in terms of the other three. So the ones with the pivots are linearly independent. The other one is not, is dependent on the others. Did that. Vector spaces have the standard basis, which is one in each slot, where you put one in each slot. So if I'm in R3, I've got 1, 0, 0, 0, 1, 0, 0, 0, 1. This is known as the standard basis. Physicists say I, J, and K. Yeah, I don't care about that. That's physicists. I say E1, E2, E3. If we're in R4, you have ones in each of the spots. I can do the same thing with matrices. One in each of the four spots. I'm not going to do a matrix bigger than this. Oh, M sub 2, 2 means 2 by 2 matrices. I can do it with polynomials of degree less than or equal to 2. Your standard basis would be 1x, x squared. Just the different possibility. Basis examples. Okay, suppose I have these 5 vectors, and I want to think about what a basis is. They are all living in R3. So, if I put this in row echelon form, I see that the first 3 are linearly independent, and these other 2 can be written as really gross linear combinations of the first 3. Well, if I've got something in R3 of dimension R3, that is R3. So, if I wanted a basis for the space spanned by those vectors, I could just say it's the standard basis. Looking at this one, I have 4 vectors, but I'm in R3, so there's got to be some linear dependence. If you're in something of degree 3 and you've got 4 of them, there's not enough space. Something's going to be cramped into the others. You're going to have some redundancy. So I put this in row reduced echelon form, and I get this. In fact, I see, oh, there's only 2 of them. I see 2 linearly independent vectors, and the second 2 can be written in terms of those. So this set of vectors, column vectors, spans a space that's 2-dimensional, and the basis I can write as the first 2 columns. And you could tell I did that with my little itty-bitty pen. So that's how you do a basis. Hopefully I put kind of a lot of ums and ahs in there. I'm sorry. Hopefully you can follow it. You can slow it down or redo it, but I think it's okay. So, good luck.